this is the outline for chapter 29. So we'll talk about the magnetic field generated by current, and we will further talk about the force between two parallel currents, because it means that if a current can generate magnetic field, so if we have two parallel currents, then when you consider one of the current, then it will generate magnetic field. So this magnetic field will interact with another current. So that's point so it's just an extension from the last part of the final part of the last chapter. We talk about the Lorentz force about the current. And then we'll talk about the Ampere's law, which is another law in the Maxwell equation. Then we will talk about the solenoid and toroid, which is two structures to generate the magnetic field. Then you can consider this one to be the inductor. Okay, so the next we will talk about the current coil as a magnetic dipole. Okay, so this is just an overview. We have seen this in chapter 23 when we talk about the Gauss law. So which means that we already learned the Gauss law, although not exactly like this. We use E for the we use E on the left side, and then we have epsilon naught here. And then in this chapter we'll talk about the Ampere's law. The form doesn't look exactly the same. We'll use the B field and then 1 over mu naught here. And then in this chapter, we only consider this current only. For this term, we'll talk about it in chapter 33, which is so-called the displacement current. So this is the current in conventional sense. But this one is the displacement current. So you can regard it as the current going through the capacitor, something like that. Then in the next chapter, we'll talk about the Faraday's law, so that we basically finish all the laws in the Maxwell equation. And of course, this one is another Gauss law. We will also talk about this in chapter 32. Okay, so here is the law we want to talk about. So let's consider this figure. So it says the magnitude of the field dB, which means a small magnetic field, or the small B field generated by a small segment of current. Okay, it's produced at the point P at distance r by a current length elements ds turn out to be this expression. Okay, so let's see how we can use this one, or what does it really means. So first of all, this is a dB, which is the B field generated by this segment in red color. This is a mu naught. Mu naught is a constant, like the epsilon naught for the electricity, for the E field. So we can see here, mu naught is called the permeability constant. The epsilon naught is called the permittivity constant. Here is permeability constant. In Chinese it's called 磁导率. Okay. So this value is 4 pi times 10 to minus 7, so which is easy to remember. And and the value is approximately like this number. This is the SI units. And as I mentioned, when you just look at the equation in the electromagnetism for some formulas for E field, some formula for B field, and as I mentioned, for the equation, the equation for E field, and then we will generally use E and then epsilon naught. So usually the version in B field for the magnetic field would be like we change E to B and then change the E to 1 over mu naught. So we have the reciprocal for this constant. So at that time we have the k constant k for the E field like 1 over 4 pi epsilon naught. So if we just follow this rule, then it becomes mu 0 over 4 pi here, mu 0 over 4 pi here, because epsilon naught become 1 over mu naught. So this mu naught will go to the top, which is like this. So we can see this term here. And yeah, so that's why I said this number is easy to remember, because we have 4 pi here, and then we will cancel with this 4 pi. So this whole term will become 10 to the minus 7. Yeah. And then the foreign terms will be I ds sine of theta, and then out theta. And then the theta is the angle between the direction of ds and also the point from ds to the point P. Point P is what we concern the dB at this point. And then R is the vector from the ds. Yeah, because this segment is so short, so you can consider it a dot. So we can connect this dot with this dot. And then the length is a vector, and then the direction is from ds to this point P. And then R hat is the unit vector. So you can simply imagine we have sine of theta here. So we should be related to the cross product. And the angle between and the angle theta is between the I, this segment. This is ds. This is I times ds. I times ds is this blue vector, and then r hat is the unit vector in this direction. So theta is somehow like we cross ids to this r hat, yeah, something like that, and then over r square. So if we really want to write it in the vector form, it will be like I ds cross r. ds is in this direction and then cross to r. So it will be, yeah, for this one we'll point into the page. Okay, so we use r hat here so that we still keep the r square in the denominator. So this is the vector form of this equation. So which so this cross product includes this sine theta terms. Okay, so far, and then so this law is called the law of Biot-Savart, or we can call it a Biot-Savart law. Yeah. Okay, so actually this is a law, so don't ask why it would be like that. We cannot prove a law. If you learn the mathematics good enough, you know, theory we can try to prove, but for law we cannot really prove. We may be able to use some other theory to derive this one, but yeah, not necessarily okay. So for this law, try to accept it. It is somehow like the physician try to do some experiment and and conclude this is the law following the experiment result, something like that. Okay. So yeah, so next we talk about the magnetic field generated by a current. So this is a special case. So you can try to remember this equation because it will occur frequently. Even though in the quiz and exam will provide this to you, but actually you can simply remember this equation. So let's see what it is. So it says for a long straight wire carrying current I, the Biot-Savart law gives the magnitude of the magnetic field at a perpendicular distance out from the wire. So which is shown as this equation. We will try to prove this one in the coming slides, but let's see what it really is. So for this figure, you can see This is a circle with a cross. So it means that this is a current going into the page. And the length of the wire is infinitely long, infinitely long. So this long means infinitely long from negative infinity to infinity. Although practically it can't be like that, but yeah, that's the case we assume here. And then for this case, it will generate the magnetic field, the green lines are the magnetic field lines. So you can see the region close to this current is denser. So the B field here is stronger, and then the B field far away from the current will be weaker and weaker. Okay, so here the magnetic field, for example, at this point, so for example, for this point, the magnetic field is considered like the distance between the current, and this point is R. So the magnitude of the B field here is mu0 is the permeability constant just mentioned, and then I is the current here, and then 2 pi is a constant. R is the distance between these 2 points, and then this is a vector, of course, and then the direction should be the tangent line. So this is the B at this point. Okay, so which is a tangent line to this circle. So all these B field line are concentric circle. And then the direction will follow the right hand rule. It means that how to use the right hand rule here, you try to use your thumb pointing to the direction of the current. Like this, you try to use your thumb pointing to the direction of the current. This is into the page, so you use your thumb pointing into the page. And then your finger will in the clockwise direction, which means that the B field is rotating clockwise. So this is how we use the right hand rule. You use your thumb. Your thumb follow the direction of the current, and then your forefingers is the direction of the B field. Yeah. So we generally will use 2 ways to for the right hand rule. One way is the cross product. You use your forefinger pointing to the first vector, and then sweep to the second vector, and then your thumb will point to the output vector direction. And then this way is if we have a current, then you try to use a thumb pointing to the direction of the current, and then the magnetic field will follow the direction of your forefingers, like this. So here is also said that likewise for the semi-infinite straight wire, which means that it starts from 0 to infinity, and then the magnitude of the magnetic field at the perpendicular distance from the wire will be this one. This one is actually half of it, because due to the symmetric, so we only have a half of the magnitude. Okay, so here it shows the proof of this equation using the Biot-Savart law. Okay, so here we try to draw the current like this. It starts from the negative infinity to positive infinity. Okay, so here we use the Biot-Savart law like this. dB equals mu0 over 4 pi times IDS sine of theta over R squared. Okay, so here let's try to maybe we pick this point to be the 0 point for this axis, and then this is the ds. This is the ds we concern. So for this small segment of the current, it will generate a B field at this point. Okay, so it will look like it will look like this actually db actually b is nothing but it would be something like integration of dB from negative infinity to infinity. So the original point should be like this. dB is a small segment. It's the B field generated by this small segment, and then we try to add the whole lines by integration from negative infinity to infinity. And then actually this one is symmetric. This one is symmetric. So so this one will be like 2 times of this integration from 0 to infinity. So we just cut it by half because you can simply imagine this part you can find also a ds symmetrically. If it is a s, then this ds will generate the same dB, because it will not cancel anything, because you can imagine we have ds here, and then we have out here. So the direction at this point would be like ds cross out. So it will be pointing into the page, and so as this point. This point, ds also pointing upward, and then out point to this side. So we have a cross product, so also db point also point into the page. But you can imagine the magnitude will actually be the same. So this integration will be symmetric. It's an even function. This is an even function. So we just cut it by half and then multiply by 2. Okay, so we can plug this term into here. So this 2 will cancel with this 4 pi. So we only have a mu0 over 2 pi here. And then we have sine of theta. Sine of theta is related to it's related to ds, and also r square is also related to ds. So we still keep this 2 term inside, and then we need to do some variable change of variables. So actually you can see this is s. Maybe I can just remove this part so that you can see it more clearly. Like this. So you can see here, this is s from 0 to this ds. This distance is s, and then this is r, which is a known value. This small r is not a known value. So we need to express r in terms of s and also r, because s is related to this ds. So we have r equals square root of s squared plus r squared, according to the Pythagorean theorem. And then sine of theta is actually this one, because it is the angle between the ds and also r hat. So this is theta. And sine of theta is actually equals to sine of pi minus theta. When you learn the trigonometry in high school, you know this equation. And then so sine of pi minus theta, which is actually this angle. This is pi minus theta. So sine is this side, the opposite side, divided by this hypotenuse. So this capital R over small r, and then small r is this square root value. So sine of theta equals to this term, and then we can plug these 2 terms into here, so that we will get so we have r theta. R square in the denominator, so that we have this term square, so it becomes x squared plus r squared, and then multiply by this one. So altogether we have a 3 over 2 power, and then also we have this term in the denominator. So this is the term we can calculate, because r is a constant. We only have this s in this ds integration. So we can do the integration now. So this one is it's not difficult to do, I think. Of course you need to do some change of variable, like yeah, actually you should use something like S equals R times tangent of theta, and then you change it to there, and then yeah, maybe you still need to do some yeah. Then you can have a ds equals r secant square theta d theta, something like that, to do this integration. And then finally the answer will be like s over this square root of s squared plus capital R squared, and then we evaluate from 0 to infinity. So when you plug in infinity, s equal infinity, this one will be 1. This one will be 1, because if this is infinitely large, this one is very small, so we have r squared, take the square root, which will be s, so we cancel it with this one. So when we evaluate from at infinity, this term will be 1. If we evaluate at 0, so this term is 0, this is finite, so this is 0, so 1 minus 0. So the answer will be actually this term. Okay. So far, any questions? Okay, no questions. Yeah. Okay, so this is another case. So here, yeah, if we have a current, but the wire is like the circular arc, 弧. Yeah, so the magnitude of the magnetic field at the center of the circular arc can be written like this. So here we have a special case. If the current wire is like an arc, but in this case we can only calculate the point at the center of this arc easily. For other points, yeah, we don't have a very good looking expression, but for this case, actually all the point in the space, you can really find the point, because this wire is infinitely long. So no matter which point you pick, you can draw a perpendicular to it, and then you can find it out, and then for the upper part of the part and the lower part, you can still see the infinitely long wire. But for this one, we can only calculate the B field at the center of this arc, and the expression will look like this one. The derivation for this formula is like this. So you can see this is the Biot-Savart law as we mentioned. The only difference is that we use capital R here because it is a circular arc, so R for this case is a constant. And then so B here is dB integrate from 0 to phi. Phi is the angle of this arc, the angle of this arc. And then yeah, so we consider the Biot-Savart law like this. So for example, for this point, ds is a tangent line to this arc, and then the r will be from ds to the center. So this r is the radius. Or capital R. But here we only use a r hat, small r hat here. And then actually ds cross r will be pointing out of the page. ds cross r, dB will be pointing out of the page. So using the right hand rule, ds cross r pointing out of the page. Okay, and actually, as the I is, will be the same for the whole line, and also R, capital R is also uniform for the whole line. So actually all the terms are constant, so we can just put it out, and then the only things we have is the ds from 0 to phi will be nothing but so this ds is nothing but r d phi pi. D phi pi is, you can probably consider this is the 0 degree, this is phi, so we integrate this from 0 to phi. So actually this is the length of this segment, which is actually equal to the radius multiplied by this angle in radian. So we have r times phi for this integration. R times phi for this integration. So this r will be partly cancelled with this r square. So we have 4 pi r in the denominator, and then we have mu 0 I phi in the nominator, in the numerator. So this is the expression, slightly different from the previous one because we have an angle for this arc here. And then the special case for this equation is that if it is a full circle, which means that phi is 2 pi for the whole circle. So this 2 pi will be cancelled with this one, with this 2 pi. So we have a mu 0 I over 2r. So we don't have this pi in the denominator. But for this one, we have mu 0 I over 2 pi r for a long straight wire, infinitely long wire. And for this one, we have mu 0 I over 2r, only 2r, for a full circle of current wire. Okay, so far any questions? Okay, so let's take a look at this sample problem. Okay, so the wire carries a current I and consists of a circular arc of radius r and central angle pi over 2 radian, and two straight sections whose extension intersect with the center C on the arc. So what magnetic field B does the current produce as point C, which is actually the center of this arc? Okay, so this one is pretty easy. So you can consider these three segments one by one. So this is segment 1, this is segment 2, this is segment 3. So for the segment 1, suppose you have a ds here. This is ds. And then so r should be start from this point to the center. Which means that r head and ds will point to the same direction. Ds and r point to the same direction, which means that the cross product between them is 0. So we have a r head ds cross r head. Don't really remember. Let me see. Yeah, we should have ds cross r head. ds cross r head should be 0 vector. So we don't have any dB, which means that a dB will be 0 for segment 1, and similarly for segment 2, ds and r head will point to the opposite direction, which means that theta equals 180 degrees. So sine of 180 degrees is also 0. So for segment 2, we don't have dB generate at point C either. So the only remaining part is part 3 with the segment 3. So we can simply use the simply use the, so actually we can write it as a dB1 equals mu 0 over 4 pi times I, and then ds sine of theta, and then over r squared. And then here we know that theta equals 0, so this whole term is 0. So B1 is nothing but 0, and similarly B2 equals 0. Here theta equals 180 degree. So we can just use the same equation to see that. And then for B3 we can actually use mu 0 I phi over 4 pi r, as we show in the previous slide. Okay, so here mu 0 I times phi is pi over 2, and then over 4 pi r. So this pi and pi can be cancelled. Pi and pi will be cancelled. So we altogether have mu 0 I over 8 r. Okay, so in total we have B1 plus B2 plus B3 to be mu 0 I over 8 r, which is the answer to this question. Okay. And of course, if you really need to determine the direction of the B field, you can use the right-hand rule. So even though this segment is not a straight line, it's curvy, you can still use the right-hand rule. You can use your thumb, follow the direction of the current. Although, it's not straight, but you can still somehow pointing, maybe, actually this is the tangent direction. So this is the direction of the eye, and then your forefinger will follow the direction of the B field. So here your thumb pointing to the right side, so your thumb will pointing into the page. So the B field at point C will be pointing into the page. The page. Okay, so next we consider another case. Now we have two long parallel wires carrying current I1 and I2 in opposite direction. So you can see in this figure, for I1 it is a dot, so it is pointing out of the page, and this one I2 is a cross, so this current is pointing into the page. So what are the magnitude and direction of the net magnetic field at point P, assuming the following values, I1, I2, and D. I1, I2, and D. Okay, so this is easy because we only need to consider the magnetic field or the B field at point P. So we have two wires here, so we can just calculate the B field corresponding I1 and I2 one by one, and then we add them together. So first, we try to calculate B1. The magnitude of the B1 is easy because this is nothing but a mu 0 I1 over 2 pi of a capital R, because this is a right angle triangle. So this is R, this is R, and then this is D. And then we can simply see that D equals square root of 2 capital R. Okay, so so this is B1, and also B2 equals mu 0 I2 over 2 pi R. Okay, and then we have R equals D over square root of 2. So which is like 5.3 over square root of 2, which is 3.75 centimeter. Okay, so in this case we need to add these two B field together, but actually they are not pointing to the same direction, so we must consider carefully. So let's consider the direction generated by I1 first. Okay, so the current is pointing out of the page, and then we consider the B field at point P. So we use we need to determine the direction at point P by R, ds, which is pointing out of the page, and then R head is pointing this way. So you can see the direction will be like this is ds pointing out of the page cross to this side. So this is the direction of B1, which is shown in this arrow. And then similarly for I2, the current is going into the page, and then R is from this current pointing to this point P. So which is like you use your finger pointing into the page and then cross to this side, and then your finger point to the top right. So this is B2. This is B2. And you can simply see that B1 and B2 are perpendicular to each other. So we can see that the total B field, B should be the square root of a B1 square plus B2 square, like this. Okay, so this term will be like mu 0 over 2 pi capital R, and then we have a square root of I1 square plus I2 square. Yeah, because mu 0 over 2 pi R are common factors. So yeah, so if we have square and a square root, so this one can be taken out, and then the I1 and I2, we take the square and then sum together and take the square root. Okay, so we can just plug in all the values. Mu 0 is 4 pi times 10 to minus 7 over 2 pi, and then R is 3.75 centimeter. So this is a 0.0375, and then times square root of I1 square plus I2 square, which is 15 square plus 32 square, like this. Okay, so this number is 180 mu Tesla. 180 mu Tesla. Okay. And the remaining stuff is to determine the angle. Yeah, the direction, of course, the direction. Okay, so yeah, so to determine the direction, we can find the phi here and then add it with 45 degree, because yeah, this is a right angle triangle, so this is a 45 degree and this one is also 45 degree. So we calculate the phi first and then add it with 45 degree, which will be the angle between the x-axis to the B field generated by this structure. So phi will be arctangent of this one. This one is B1, so arctangent of B1 over B2. So which is arctangent of I1 over I2, because you can see here B1 over B2, all those terms are common factors which will be cancelled, so the only remaining term is the I1 over I2 here. So which is an arctangent of 15 over 32. So this is 25.1 degree. So the theta is from the x-axis, positive x-axis, to the B field, which is 5 plus 45 degree, which is 70.1 degree. Okay. Okay, so let's have a 10 minutes break first and then we will continue.